Welcome to tutorial session of IEEE CICC 2020. This tutorial is entitled Low Power PLL Architectures and Techniques. I'm Mike Chen from University of Southern California. My group mainly work on different critical components of analog mixed signal design, including the phase lock loop. Today, I'm going to share some of our past experience, particularly for the low spurious tone performance PLLs. Here's the outline of today's tutorial. First, I will describe the basics of PLL architectures. Next, we will overview different sources of spurious tones. Next, we will go over different spur cancellation techniques, where I will divide into two different categories. One category is what I called as direct spur cancellation, where we actually directly mimic the spurious tone information and we cancel it. So within this category, we have three different types. We have single tone cancellation, we have multi-tone cancellation, and then I will describe a more advanced version, which is a pulling signal cancellation. Another type of spur mitigation is based on the dithering techniques. So I will also separately discuss those categories. Finally, I will conclude this tutorial. Shown here is the popular analog phase lock loop architectures. First of all, we can see there's an oscillator shown in these figures. It basically generates the clock that a frequency synthesizers should generate. The problem with a free-running oscillator is that the frequency of that oscillator is very hard to control, especially under the process, voltage, or temperature variation. And therefore, typically for a phase lock loop, we have to put these free-running oscillators inside a negative feedback loop. As we can see here, a typical feedback loop is involved with some frequency dividers, where we would divide down the oscillator output to a lower frequency, and then we compare this divided down frequency with the clean reference input clocks. By comparing these two clocks, we can compare its frequency difference and the phase difference, and we basically turn that into some control voltage to control the oscillators. Now, from this phase information to the voltage information, in the analog PLL, we usually deploy a charge pump circuit and a loop filter to actually filter out the noise information. So as we can see here, basically what happens is most of this control loop is occurring in the analog domain. So as we can imagine, this applies to any circuit non-ideality that we usually face for analog circuit design. So just as examples, we have headroom issues, we have matching issues, we also have a noise that present in the circuits. In the loop filter, we may be facing the leakage issues, and because the loop filters typically is done by the resistor and capacitors, they are typically also very area consuming. So all those design constraints are facing for analog phase lock loop architectures. On top of that, we also will face the external noise coming from the other parts of the circuit. For instance, today, when we implement SoC platforms, it's very easy that we would pick up some noise from other circuit blocks. For example, for the digital blocks or from other clock generation blocks and things like that. So we constantly will face those different noise coupling to the designed phase lock loop. More recently, people start to investigate yet another kind of phase lock loop architectures. So we usually call it the digital PLL, or sometimes people call it all digital PLL. This is an emerging interest in a more digital intensive design flavors. As we can see here, the basic structures of the phase lock loop does not change. we still have this free-running oscillators, and we still put this oscillator inside a negative feedback loop, except that, as we can see here, the control loop inside this feedback is actually implemented in the digital logic. To do this, we actually would need to imply some kind of ADC between the analog and digital domain. And since right now, the analog signal that we are dealing with is in the time domain or phase domain, and therefore this ADC in this scenario is usually called as time to digital converters, or sometimes people refer it as TDC. Then after the TDC, the phase information is actually turned into the digital code, and the following dividers, phase frequency detectors, and the filters can all be in the digital logic. And as we all know about the digital circuits, there's no leakage and there's no noise other than the finite wavelength effect of the digital logic. And because of the Moore's law, this digital implementation is also very area effective. Finally, because everything is in digital domain, it can also be very flexible. For instance, sometimes we would like to change the dynamics of the phase lock loop to be type 1, type 2, or type 3, and this can all be easily done in the digital logic. Note that here, since the output of the digital filter is simply a digital code, so we have to convert that back to the analog domain, for example, to an analog voltage, in order to control these oscillators. So typically for a digital PLL architectures, we do need some kind of digital to analog converters. And this obviously will become an overhead, for these architectures, because we do need to, do this extra digital to analog interface conversions, and which also means that any non-idealities with the DAC can also be injected to the digital PLL loop. On the ADC side, here, this is just mimicking a typical ADC, and therefore there could be also a noise associated with that. There can be a gain errors associated with that. So there will be requiring a lot of times additional calibration loop to actually compensate that. But the bottom line is that, once you are able to do a good ADC and the DAC for this PLL, we can turn all the computing logic in the digital domain, which can really benefit from the Moore's law. Now, if we look at the evolution of the digital PLL in the past decades, I would roughly divide that into 3 different waves. In the very early on stage, if we look at the digital PLL publications, they are mainly focusing on reducing the silicon area. And a lot of times they really take advantage of technology scaling. In fact, a lot of times they would compare the counterparts of the analog PLL with the converted digital PLL, and just to show that how much area they are actually saving. In the second wave of the digital PLL, I would say that people are already trying to close the performance gap to the analog PLLs. As we mentioned before, for digital PLL architectures, it actually involves additional digital to analog converters and the time to digital converters. So a lot of times people are really spending efforts in reducing the overhead of those additional interface block. So you can see that in the second wave, people are showing a smaller and smaller gap between the digital and the analog PLL. Today, I believe that we are already in the third wave, which means that we are actually pushing the digital PLL performance to go beyond the analog PLLs. A lot of times, people actually spend time to focus on reducing the cost of the TDC and also to relax the calibration requirement of the TDC. And more importantly, because the signal processing right now is happening in the digital domain, so there's the abundant DSP opportunity there to help us to do something that, an analog PLL cannot do. So for example, we may be using that capability to actually further reduce the spurious tone levels, which will be one of the key focus of today's tutorial. Okay, so now that we already overviewed the high-level architecture of the analog and digital PLL, the next practical question that we need to ask ourselves is, which one should I use? And that really depends on what technology that you are having and what PLL specification that you are facing. For example, if the technology that you are using is very fast, which means that you have a very small inverter delay, then I would say that digital PLL presents a very promising solution. Because later on we will see that a lot of times these so-called time-to-digital converters really rely on the resolution of an inverter delay. On the other hand, if the PLL output frequency requirement is very, very high, that typically also suggests that we need to use a very fine time-to-digital converters in order to have a low in-band phase noise floor. So, a general guideline, if you are actually using an older technology or your noise requirement is very stringent, I would say that the analog PLL remains a very attractive solution. However, if you really care a lot about the area consumption, the power consumption, and the portability between different technology nodes, a digital PLL can be very attractive as compared to the analog PLL, because most of the digital logic can be simply written in Verilog, and you can also use all the CAD tools that's available to you to do those digital synthesis. So that's just a rough guideline of how we may choose between the analog and the digital PLL architectures. Next, we will briefly overview the specifications of a PLL design. First, we will examine the case for the wireline applications. Typically, in the wireline applications, we use the clock to generate and to decode the data symbols. So here, they usually divide the jitter into a random part and also a deterministic part. The random part of the jitters typically is related to the integrated phase noise at the PLL output, and for the deterministic part, it's usually related to the spurious tone of the PLL because it generally generates a periodic noise pattern. So as we can see here on the right hand side, this is the phase noise of the PLL. You see this noise floor. So if you look at this noise floor, we integrate the noise power that usually would yield the random jitters. And you see those spiky tones. Those are the spurious tones, and they will contribute to the deterministic jitters, which is what I show here. Typically, the spur will cause the deterministic jitters. And as you can see, if the clock that you have has a lot of jitters, then the eye diagram of the wireline communication, you can see this eye will be closing up, which is not good because it will suffer from the high bit error rate performance. What about the wireless communications? So PLL is also heavily used in the wireless communications. For example, in the transmitter side, we would usually upconvert the baseband signal to the carrier frequency. And on the receiver side, we do the opposite. We would use a phase lock loop to generate the frequency at the communication band so that we can downconvert the signal at the communication band back to the baseband for signal processing. So as here, we can see that if we have a high phase noise of the PLL, or we have the spur on the PLLs, it would actually generate these unwanted signals at higher frequency offset. So a lot of times it can actually violate the emission mask that required for the communication systems. On the receiver side, as we can see, if we have the spur right here, and if we have some blocking signals, next to your desired signals, we could also down-convert those blocking signal back to the baseband. And once those unwanted signal is down-converted to the baseband, if we look at the in-band signal to noise ratio, it wouldn't be good. And a lot of times it can degrade the performance of this wireless communication. Or in other words, the EVM performance of the system can be very poor. Okay, so now we understand the importance to keep the spurious tone low in terms of a system application, for example, wireline or the wireless. So next, we need to understand where are those spurs coming from. So here, I divide that into two different categories. One is the external coupling. The other one is internal generation. For the external coupling, usually the spurs coming from other noisy blocks. For example, it can be another digital block, or it can be another clock generators that generated for other digital circuits. And those noisy blocks can couple the spurs through, for example, power supply, or the substrate, or magnetically coupled through the bond wires, just as examples. And those noisy signals can actually cause these harmonic tones at the PLL output. Another category of the spur is internally generated. So here we have to divide that into integer N mode and also the Fractional-N operation mode. Later on, I will describe a lot more details on how Fractional-N operation mode works and why and how they generate the Fractional-N spurs. But at the high level, it's essentially whatever that Fractional-N frequency that we're dialing in for the PLLs, at the harmonics of that Fractional-N frequencies, we usually will see harmonic tones, at the PLL output. Another type of internally generated spur is called reference spurs. Essentially, if we look at the PLL output, if we look at the reference frequency offset from the carrier frequency, we usually can see a harmonic tones right there. And for analog PLL architectures, it has something to do with the non-idealities of the phase frequency detectors, charge pump, or analog loop filters. For the digital PLL, because everything is in the digital domain, so we do not have these non-idealities in the loop filters or the charge pump or the PFD. Instead, it's more vulnerable through this direct reference clock coupling. It can be coming from the supply, or it can be from the substrate. So those are the different sources of the spur generations. So just to give you an example, as we can see in this slide, this is a typical SoC platform in the modern day. So as you can see here, you have the analog portion and you have the digital portion. And as you can imagine, all this digital portion can be clocking at some frequencies, and you can see that the PLL on the analog side may be picking up those noise, through the substrate, it may be through the bond wires, or it can be through the power supply. So this one just to show you that, it's really, really difficult in today's IC implementation to actually stop those external spur coupling. In terms of the internally generated spurs, I would like to focus on the Fractional-N spur generation. And the reason is that the reference spur generation is a lot easier to mitigate, especially for digital PLL architectures, for the reason that I just mentioned, because the non-ideality in the analog circuit design is no longer exist in a digital PLL architectures. Okay, so what is a Fractional-N operation? Essentially, the way that we use PLL in the context of frequency synthesis, we essentially just generate a clock multipliers. So essentially, we like to generate the output of the PLL to be a certain ratio compared to the input reference clock frequencies. And that ratio, if we take the PLL output frequency divided by the input reference clock frequency, if the ratio is not an integer, and that will be the case where we refer that as a Fractional-N operation. So why do we need a fractional operation? So there are a couple good reasons. One is that, some system, they may require a fine frequency resolution for the clock. For instance, if we actually use this PLL to generate the clock for up converting and down converting process for the wireless communications, this wireless channel can be just kilohertz apart, which means that we actually need to synthesize a very fine resolution PLL output frequencies. And another good reason is that sometimes the system will require a higher reference clock frequency. Sometimes it's because the choice of the crystal oscillators, and sometimes it's because the system will require you to implement a very wide PLL bandwidth. So for those reasons, sometimes the reference frequency can be high. So how can we achieve that? So here I give you examples. If the output of the PLL frequency is no longer an integer multiple of the input reference clock frequencies, this can be considered as a Fractional-N operations. And here, as we can see, the ratio between F out and F ref is just by these fractional numbers. So in this case, if I can make the resolution of that fractional number to be 0.2, then I can generate this reference clock frequency as high as 5x more and still keep the same output frequencies. Next, I'm going to show you two very popular approaches to implement the Fractional-N operation. The first approach is by using a multi-modulus dividers. Basically, as we can see here, the trick is to change the divider ratio in the feedback path. Sometimes it can be divided by a factor of n, sometimes it can be divided by n plus 1, and sometimes it can be divided by n minus 1. And when should we choose these numbers is just determined by these delta sigma modulators. So we just basically keep changing this divider ratio in the hope that we can synthesize the output at exact right frequency. How does that work? So we should look at this timing diagram. So in this timing diagram, the example that I'm showing you is a divider ratio of 4.25. So here is the VCO output right here. And because it's 4.25, so we can see that the reference clock, the period here is exactly 1, 2, 3, 4 plus another quarter period of the VCO output. And by the way, the VCO here, note that typically in the digital PLL architectures, we call it DCO because it is the digitally controlled oscillators. So nevertheless, we can see that the rising edge of the reference clock will start to drift, from the rising edge of the corresponding DCO period. So if we just use the constant feedback divider, for example, if we always divide by 4, so we can see that the edges right here will just keep increase and increase. So that is not very good because the way that phase lock loop works is that we should always compare the input with the divided output phase. So instead, what we do is that we will use the delta sigma modulator, and sometimes we will divide by 4, and sometimes we will divide by 5, so that you can see this rising edge here and the rising edge here. It would try to follow the input reference clock. So that's the whole idea of using a multi-modulus Fractional-N operation. So if we use the multi-modulus Fractional-N architectures, where does the Fractional-N spur come from? So it turns out that because we use the delta sigma modulators to select that divider ratio, that modulator by itself can actually have limit cycles. So this is actually a well-known property of the delta sigma modulators. So for instance, if we actually use the first order delta sigma loop, and we only use a 1-bit quantizer for that delta sigma modulators. And if we inject a DC input signal, for example, 1, 7, then the output of this delta sigma modulator will be 1, 1, minus 1, 1, minus 1, 1, and minus 1. And then it will just keep repeating by itself. So unfortunately, if we look at the spectrum of these repeating patterns, we are going to see this harmonic spurious tones happens at integer multiple of the fs divided by 7. And the fs here is essentially the sample rate of the delta sigma modulators. And unfortunately, because of this repeating patterns, it will actually show up at the PLL output. The second approach to generate the fractional-N frequency is so-called frequency accumulation approach. So as you can see here, instead of doing the delta sigma modulated divider right here, we actually just use a constant divider in the feedback path. And instead, what we are doing is that we just try to accumulate that frequency offset that we are trying to generate and inject at the output of these phase frequency detectors. So essentially, by doing this, we are actually inject a frequency offset in the digital domain, and hence we can control the output frequency of this PLL. To understand how this frequency accumulation type of fractional-N PLL works, we have to look at the timing diagram. So in this case, I'm using the exact divider ratio, which is 4.25, exactly the same as the case I showed you previously. So in this type of PLL architectures, in the feedback divider, we are going to use a constant value. So in this case, we are always divided by 4. So if that's the case, if we observe the rising edge of the reference clock and the rising edge of feedback clock, we can see that the phase difference here will keep accumulating. So for instance, in the beginning, the phase difference can be delta tau, and the next rising edge will be 2 times delta tau, and the next time will be 3 times delta tau. And that is exactly why we will accumulate the frequency offset and inject it at the output of the PFD. In other words, we are actually intentionally guiding this phase drift to be exactly the rate as what we wanted. Now, through the simple algebra derivations, we can prove that by introducing this phase drift between the reference clock and the feedback clock, we can write out this relationship between the reference clock period and the feedback clock period, which will be off by a ratio of 1 plus k. And in this case, if we multiply k by the period of feedback clock, it will be exactly this delta tau number as I mentioned earlier. Now, if we further derive the math, we know that the DCO frequency will be exactly n times of the feedback clock. So if we multiply by this n factor with the previous derivation, we can show that the divider ratio of this entire fractional-N PLL will be n times 1 plus k. So in other words, by changing this rate of the delta tau, I can change the rate of k, which means that we can determine what's the fractional-N frequency ratio that we're trying to design for this PLL. So that's exactly how this accumulation type of PLL works. So now that we see how that works, so we need to understand why would this type of fractional-N architecture would also generate the fractional-N spurs. So to understand that, we need to first look at the transfer function of the time to digital converters. As I show here, in the ideal time to digital converters, there should not be any quantization errors. So you can see that the relationship between the input phase and the output digital code will be a perfect linear line. So in this case, we can see that the quantization error is actually 0. Now, in reality, we have to design this time-to-digital converter with a finite resolution. So in this case, this is just exactly the same as the A to D design, where we can see this finite quantization step. So in this case, unfortunately, it will show up as a certain quantization errors. And just to make things worse, in real life, for sure, there will be additional mismatch, associated with this time-to-digital conversion. So in other words, there's going to be a certain DNL patterns associated with this time-to-digital conversions. So as a result, we can see that in real life, the quantization errors can be larger compared to the ideal n-bit TDC quantizations. So with the fractional-N operation, as we showed in the previous slides, essentially we'll be ramping this input phase linearly from 0 to a certain maximum value, and it will wrap around back to 0 and so on. So essentially what happens is that we will be sampling these quantization errors for this digital fractional-N operation. So because we are sampling these repeating error patterns, the output of this fractional-N quantization errors is also repeating by itself. So as we know, whenever we see the noise is repeating by itself, for sure we are going to see this harmonic spurious tone that will show up at the final PLL output. And that is why in the frequency accumulation type of fractional-N PLL architectures, we will also see these fractional-N spurs. The mechanism here is a little bit different from the multi-modulus type, where the spur was mostly coming from that delta sigma modulator itself. Okay, so now that we understand the sources of those spurious tones, it can be coming from externally and it can be coming from internally. And now the next question is, how do we actually cancel them out? So we are going to take it step by step. We will start from a single tone first. So shown here is the first prototype that we have done numerous years ago, where we actually try to use this so-called gradient-based spur cancellations that we would inject in this loop of the digital PLL architectures. And in addition, we also have this injection locked TDC, where we would inject this additional ring oscillator to the main oscillator of the PLLs in order to avoid any additional calibration requirement. But today, for the sake of the tutorial, we will be mainly focusing on the spur cancellation loop. Okay, to understand how this spur cancellation works, let's first look at a very ideal scenario where there's no interference in this PLL system. Doesn't matter it's coming from externally or internally. So in the ideal PLL, it should actually just give you a certain DC value, a constant value that will pin this oscillator to oscillate exactly at the target frequencies. So again, there's no interference in this case, so that's why the value that you should get should just get desired DC value. Next, we are going to inject the interference to the PLL. So in this case, just for illustration purpose, we intentionally inject a sawtooth patterns at the input of the PLL, which is coming from the reference clock path. So because we have this TDC, so what is going to come out at the output of the digital filter, what we're going to see is actually a quantized version of this sawtooth patterns. Okay, so the whole idea of this spur cancellation is that we are trying to see whether we can have this magic digital signal processing box where we can estimate this interference, in this case it's a sawtooth in the box, and then we can duplicate this sawtooth path and we can cancel it out before it goes to the digital filter. So in this case, as we can see, this sawtooth pattern will never reach to the DCO in this case. And if it doesn't reach to the DCO, then the output of this PLL will be free of the spurious tones. So that is just the high-level idea of this concept of spur cancellations. So in reality, the way that we do it is that first we need to duplicate that spur source. In this case, because we are only focusing on a single spurious tone. So what we are having is basically a digital sine wave generator. So here in this case, we call it as an interference replica. So now that we can generate the frequency of that spur, however, there are still two things that is unknown. So one thing is we don't know the magnitude of that sine wave, and the second thing is unknown is the phase of that sine wave. So in this case, we propose to use a gradient descent algorithms that will actually go back and adjust the magnitude of this replica interference and the phase of this replica reference, so that after we cancel it out, which is shown here, one is coming from the output of the PFD, and the other one is from this replica path, and assuming the amplitude, the frequency, and the phase would all match, and then we will force this error term to be 0. So that's exactly how we formulate the adaptive filter loop to basically adjust the right magnitude and also the right phase. And the way that we do that, is doing this iterated loop to actually find the optimum value. So one way to do this adaptive loop, is through this so-called gradient descent algorithms. This is a known technique in many other signal processing systems. And as we can see here, it's somehow involved with the error signals and the gradient of the output to the amplitude and also the gradient to the phase. This approach will work fine, especially if we would like to converge faster. So gradient descent is actually a good approach. But however, as we can see here, the computation here will be a little bit high, because not only we need to do these multiplications, but also we need to find the derivative functions. So it turns out that in this prototype we actually use coordinate descent instead, just to reduce the computation complexity. So in other words, we would only update the amplitude and the phase with a fixed step size, instead of having this variable step size that dependent on the gradient and the error. So to see how that works, here I plot this trajectory in amplitude domain and the phase domain. So as we can see here, our initial guess of the interference replica can be way off, from the ideal value, which is shown in the center right here. So basically, the whole iterative loop is to force us to start from the initial guess and eventually will converge to the center, which is the optimum value, which would yield a more optimum spur cancellation. So as we can see here, basically the way that we work is that, we start from our initial guess, and then we will compute if we increase or decrease the phase a little bit, or we increase or decrease the amplitude a little bit, and we would calculate what is the residue spur energy that will be remaining, by doing this 5-point calculation. So as we can see here, we basically need to calculate the error energy that associated with different phase and magnitude offset. So by doing this, basically what we would do is that we would pick the lowest error energy among those 5 dots. So for example, if by shifting these phase errors going to the right will give me a lower error energy, then basically the next iteration, I will force this phase to be shifted by this amount. And if that's if the low energy turns out to be, reducing the amplitude, then I would go from this current point to the next point, and so on. Okay, so basically, as you can see, it's basically, going through this 2D domain. So that's why, it's called coordinate descent. Basically you limit your degree of freedom to basically stay put or go up, down, right, or left. So that's the basic of the coordinate. So here, just to show you, exactly how we can do this coordinate descent altogether, in both amplitude and the phase domain. So basically, you can see here, every time what we would do is that we would either, shift in the phase domain or we would shift in the amplitude domain. But no matter which one we take, eventually we would converge to the optimum point where we would minimize the error energy, in the amplitude domain, and or we would also, minimize the error energy in the phase domain. So which is shown in the blue dot. So that will be the convergence point that we are looking at. So after this gradient descent search algorithms. Okay, so in reality, when we calculate the error energies, we need to be a little bit careful because if we just look at the RMS errors at the output of the subtractions, we could be calculating the error energy of the random noise, or I could be calculating the error energy associated with other spurs that I'm not trying to cancel. So as a result, there's one thing that we need to do before we do this energy calculation, which is the correlation. Okay, so basically we need to do a correlators. So we need to correlate exactly at the frequency that we are looking at. So note that, in this case, we are only looking at the single spur calculation. So in this case, we know what spur frequency that we are looking at. So for example, as I mentioned earlier, for the Fractional-N spurs, we would know exactly what the harmonic tones that you would generate. So you know that in advance. So you basically would correlate against that particular frequency. So if you do a correlation with that frequency, so this is essentially doing the mesh filtering at that particular frequency that you're trying to extract, then you can do this mean square errors of that energy. So by that, and then you do for both I and Q, and then you sum them together. So basically you can find the estimate of that error magnitude. Okay. So basically this is essentially doing the IQ mesh filter. So by looking at by deriving those error magnitude, then we can, plug in that the coordinate descent algorithm that I showed you earlier. Okay, so here is the implementation of that coordinate descent algorithm. So as we can see here, we basically use the direct digital synthesis that we synthesize the current amplitude and phase sine wave, and a little bit phase shift version, and also a little bit amplitude shift version. So basically, you're always looking for 5 dots, and the output of those 5 DDS, you generate the corresponding sine wave, and then you go through the correlators, and then you will find the energy, right, by doing this mean square errors, and you always pick the minimum error energy, right, and then you would just readjust what's your current samples, right? So if this is as I said earlier, if this phase offset give you the least error energy, then you will recenter this to here, and then you can always find the next iteration directions. Okay, so basically this is how we do the adaptive loop, and then we always select the best one to perform the subtraction in the PLL loop, as done by this mux, this 5-to-1 mux, and we select the best interference waveforms, and we subtract it. So that's the actual implementation, and as you can see here, everything that I point out here is all in digital domain. So we basically you can just write a Verilog, and then we can synthesize, through the commercial CAD tools. Okay, just to show that how that works, this is a time domain waveforms of this spur cancellations. So as you can see here, if we don't do any cancellation, and then if we look at the phase detector output, we can clearly see this interference, going on right there. Now, as we start to, enable the cancellation, in the beginning, you are going to see this, misaligned interference replica. So that's why you can see in the beginning, the cancellation effect is not very good. But after you find the right phase, which I shown here, and also the right magnitude, you can see that, as the replicas start to align with the actual interference, then you are going to see the reduction of the interference that will show up at the phase detector output. So once you reach to that state, and then sure enough, that will mean that, the output spurious tone would also get reduced at the PLL output. And on the right-hand side, we show the case where, without the cancellation, and once we enable cancellation, we can see that, in the beginning, you cannot really find the right settings. And once we find it, it will actually, to go to a very low values. So here's the prototype that we did. It was done in 65 nanometer CMOS. And you can see that, this digital core, houses those, spur cancellation loop, as I just described. And this is the proof of the measured results. So you can see that, before we enable that gradient descent spur cancellation, you can clearly see there's a huge tones right there, okay, shown in blue. And once we, enable that, spur cancellation, and then we can achieve as much as 43 dB cancellation. And note that, in this case, it is a true spur cancellation, which means that we actually create the replica of this spurious tone, and we try to cancel it out. So this is just to show you how effective it can be. And by that measurement, we also try to, sweep different spur frequency. And then you can see that, before and after cancellation, you can get more than 20 dB, cancellation, through this approach. So it just shows that, how effective, that, spur cancellation loop, can work. And note that, the actual, accuracy that you can achieve, for this spur cancellation, really also depends on what's the step size that we do for that coordinate descent search. So the finite step size will lead to a better cancellation, but of course, if you do that, it will just, trade off the convergence time. So meaning that it will take a longer time for you to fully cancel the spurs. So those are just the trade-off, and we were pretty happy, with that result, because that was the a true, spur cancellation that we can, for target, frequency, and we can know it out. Here's the performance summary of that prototype, and we were able to achieve, a pretty low spurious tone, minus 86 for the reference spurs, and also with DNL of 0.55 LSB and the phase noise of minus 128 dBc, and with the spur cancellation as I showed you in the previous slide. Okay, so here's a summary and compare with the state of the art. So that was the just to show that we actually use this gradient-based cancellation, and we show that we can cancel for both internally generated spurs and also externally coupled spurs. So in both cases, we were able to demonstrate that's a true spur cancellation for the target frequencies. Okay. All right. So the lesson learned, from that, prototype, is that, we recognize that the digital PLL actually provides a new design potential. So you can apply a lot of DSP-enabled techniques, and then also that single tone spur cancellation can really achieve a pretty high level. In some cases it's more than 40 dB cancellations. And this is actually a true cancellation without any dithering, and it performs this orthogonal cancellation, which means that if I have a two spurious tone right there, and if I target for the spurious tone 1, and I can just cancel out the first spurious tone, while the second spurious tone will stay intact. So later on I will show you why that's very important, because that's how we can further extend the concept of this. Okay, so far, I've been focusing on canceling the spur for a single tone, but in reality, as we all know, the spur usually come in pairs. In fact, a lot of times they come in harmonic relationship. So just as an example, remember that I show you for the Fractional-N spurs, it always comes at integer multiple of that fractional frequencies. Okay, so that proves that it is a very common scenario where they will come in harmonic. Another scenario is that the spur may even come in non-harmonic relationship. So in this case, even though there's F1, 2F1, 3F1, but you see this F2, 2F2, and 3F2, and so F2 is not an integer multiple of F1. So this case can happen, for example, when you have another PLL, operate, and it can couple that, to your PLL, right? So basically, in the SLC platforms, you have other noisy blocks that can couple to you. So this could potentially happen. And then this is going to be more and more serious in the future, because when people are integrating more and more functionality on the single die. So those are the real scenario. And now if we only do a single spur cancellation, this is what we are going to end up with. As you can see in this slide, let's say I have a spur at spur 1 frequency, and I have a second one in the spur 2 frequency. And because of the orthogonality that we approved in the first prototype, what we could do is that we can just duplicate the entire cancellation engine, which means that we can duplicate that DDS-based and the coordinate descent cancellation engine for the spur 1, and we duplicate another one for spur 2, and so on. As you can imagine, the problem with this approach is that if I want to cancel out all the harmonic, so let's say from first harmonic to fifth harmonic, then I need to duplicate 5 times. And then if I have another non-harmonic relationship of the spurious tones, then I probably need to duplicate another 5 DDS-based cancellation engine. So it turns out that there will be too many blocks that we need to duplicate, and that significantly increase the overhead of that approach. So the bottom line is that we do need a better approach. So now let's step back a little bit and look at the timing waveforms of a harmonic relationship spurious tones. So as we can see here, whenever we have a harmonic relationship of the spurious tones, the bottom line is that it always has certain period that this noise pattern will repeat. So as I show here on the left hand side, you see this wiggling waveform right here. They always repeat at a certain period, which I call it D, capital D period. Okay, so if we look at the Fourier transform of these noise patterns, we will see the fundamental frequency of this pattern, and the second harmonic of this pattern, and the third harmonic of this pattern. So let's first look at the fundamental frequency of this pattern. So sure enough, we are going to see some kind of disturbance at the frequency of this capital D, which is the fundamental frequency of this repeating noise patterns. And we are also going to see the second harmonic of this noise pattern. So you can see that the frequency here is actually twice of the the fundamental frequency. And likewise, the third harmonic, you see the 3 period right here within one fundamental frequencies. So as you can see that, no matter what you do, you can see that, all this harmonic relationship pattern will always line up with the fundamental period of this noise pattern. So that's a very important observation. Then the next observation that we're going to do is that if we take this repeating noise patterns and we delay it exactly at that fundamental period of that noise pattern. So in this case, I'm going to delay by that capital D. So if we delay that period of that noise patterns and we subtract it by itself and we look at the output, and now let's see what happens. So first, let's look at the fundamental component. So as we recall from the previous slide, this is the waveform for the fundamental component, right? And then if we delay this by the period of this fundamental by capital D, then you can see this point shift to this point, and this peak shift to this peak. And if you look at the output, if I cancel this red curve to the blue curve, and then this, you will get the perfect cancellation. Okay, so we proved that, for the fundamental frequency, if you subtract this original noise pattern with the delay version of that noise pattern, you are going to get a perfect cancellation right here. So that's the case for fundamental. How about for the second harmonic? So remember, the second harmonic patterns, you are going to see 2 period within this capital D. So now if I delay that by the whole period of capital D, then as you can see, basically similar things happens. You see this starting point shift to here, and the peak shift to here, and the second peak also shift to here. And then if I subtract the red and blue, you also get a perfect cancellation because everything will be perfectly aligned by that period of capital D. So that means that, if you actually take that noise patterns and then delay by exactly that fundamental period, you are going to get a perfect cancellation in fundamental, in second harmonic, and also in third harmonic, and so on. So essentially, no matter which harmonic you are looking at, you will always get a perfect cancellation. Okay, so that gives us the confidence of doing this so-called feedforward spur cancellation schemes. So imagine that, here I'm showing the part of the digital PLL loop, at the output of the TDC, which is basically, delay by that fundamental period, and we subtract it out and we look at the output, and supposedly, the fundamental and all the second, third, fourth harmonic will get cancelled out. So if that's the case, then I shouldn't have any harmonic component that will reach to this DCO. So that means that it should, cancel the spur. So on the high level, it sounds very tempting to do this, but however, there is one problem. Because whenever we do this delay and cancellation, we could be also canceling out this noise, right now what I show here. Okay, and that would actually create a lot of problem, because don't forget that, this is still a phase lock loop. So we actually do need to do this negative feedback on this noise that generated by the DCO. And that's actually how the PLL loop can actually suppress the DCO phase noise. So basically, this noise part should not be canceled out. The only thing that we should cancel out should only be that spurious tones that are shown in red right here. So here I show you the case where if I don't do anything, basically the DCO noise right here will get increased actually, after this cancellation. So what should we do about this? And therefore, we propose to do averaging, after this fundamental delay element. So once we do the averaging, because the phase noise here is random, so assuming that we do enough averaging, which you can see here, it's basically just a simple add and divide by capital N, depends on how many samples that we're averaging. So basically, we would average out this noise right here. So in other words, at the output of the average block, what we should see is only this red spurious tones. So now, once we subtract this out, as you can see, the output should only show the phase noise of the DCO, which it should be, and without any spurs. And so then the output of the final DCO will just have the normal phase noise profile without the spurious tone. Okay, so that actually solved our problem of enhancing the DCO noise. Next, we have yet another problem because by doing this delay and averaging and subtract, we actually would also subtract out the DC information, right? Because the DC here going to the delay, and no matter how many averaging that we do, the DC information is still there. So that created a problem because one of the important functionality of the PLL is actually to find the right oscillation frequency. So that DC information is actually very, very important. And not just the actual frequency, but also the flicker noise at the low frequency can also sneak through, and that's not very good, because you will actually enhance the flicker noise portion of the energy. Okay, so the solution to this is that we actually need to add a DC blocking to this feedforward path. So as you can see here, we essentially have to insert a 0 at DC. So by doing that, we can solve the problem because now we no longer pass the DC information, and also we block those flicker noise through the feedforward path. Okay, so then we can get the final PLL phase noise profile back to normal. And there's another potential issue is that the spur frequency can be a fractional of the reference clock period. Okay, so this can happen, especially if the spur is coming from outside or externally, right? So let's say if the PLL under design is being coupled by another clock, by another for another digital block, that frequency may not be integer multiple of my designed PLL. So the bottom line is that this spur period is no longer integer multiple of the reference period. So in other words, we may actually need to delay that capital D by a fractional number. So in this case, we may end up to be a 4.5 period of the reference clock. So in this case, we need to somehow delay that by exactly 4.5 samples. So the way to solve this problem is that we would introduce a fractional delay filter to actually provide that fractional shift. So note that if in your application that you don't have this scenario, for example, if you are just dealing with the Fractional-N spurs, then all those periods will be exactly integer multiple of the reference clock period. Then you do not need this additional Fractional-N delay filter. Okay, so this is only the case where you might be dealing with the externally coupled spurs, and that frequency can be a little bit funny. So you cannot, just generate the integer multiple of that capital D. In that case, you may be using this fractional delay filter. Okay, so that being said, this is the final solution, to generate this, multi-tone spur cancellations in a feedforward path. So you can see that, the output of the TDC, and after subtract with this accumulated frequency offset, you will go through this DC blockers, and you go to this delay, integer delay chain, and followed by a potential fractional delay filters, and you do the averaging, and you subtract it out. So that will solve the various problems that I showed you earlier. Okay, So it turns out that, there's an additional advantage by doing this feedforward cancellation scheme, and that has something to do with the DNL of the TDC. So remember that, a few slides back, I told you about this transfer function of the TDC. When there is a DNL, you could actually end up with, larger errors. So it turns out that, even though there's a DNL, that pattern would actually repeat by itself. And again, by the period of that fundamental period of that noise pattern. So in this case, for example, if I have a frequency control word, which is the frequency offset of the Fractional-N PLL, which is 1 over 2 to the power of 5 plus 1 over 2 to the power of 7, then you are going to see a period of 2 to the power of 7, with the DNL. So in other words, if we actually delay this period, which is 2 to the power of 7, we can actually also line up with this DNL pattern, which means that, the DNL effect can also be canceled through this feedforward cancellation scheme. So that's actually an additional advantage, by using this proposed techniques for the spur cancellation. Okay. All right. So that would just prove that we can solve the spur that in harmonic relationship, right? So by delaying that fundamental period, we can cancel everything, that is in harmonic relationship. So now let's step back a little bit and then go back to the case where I proposed earlier, right? Where you have two different series of harmonic tones. So as you can see, F1, 2F1, 3F1, and F2, 2F2, and 3F2. So the problem is that, this F1 and F2 may not be in harmonic relationship. So in that case, you have one option. The option is just to find the common factors between this F1 and F2. So which means, for example, if I get this fundamental D1 period from this first series of the harmonic tones and multiply with the fundamental of the second series of the harmonic tones. So you have D1 and D2, and if you multiply them, so basically, you can for sure find a common factor of these repeating patterns. Okay, so in this case, as I show you in this example, if let's say the first noise pattern is repeating at 127 samples, and the second series of the harmonic spurs are repeating at 128 samples, then we could actually use a delay of 16,256 delays to implement this feedforward cancellation. So it will work. It's just that the problem is that this is way too many delays, and then that can actually kill the implementation of this feedforward cancellation. Okay, so how can we solve that issues? So it turns out that, this is a little bit similar to what I showed you earlier about the orthogonality of the single tone cancellation. We can actually, cascade this cancellation stage one by one. So for example, we can apply the first feedforward, multi-tone feedforward cancellation loop to take care of the first harmonic relationship of the spurious tones. So meaning F1, 2F1, and 3F1. It will be taken care by this first loop. And for the second loop here, we will be canceling out F2, 2F2, and 3F2. So as you can see here, we no longer need this D1 times D2 delays for that feedforward cancellation. So instead, we just need D1 for the first loop and D2 for the second loop. So in total, all we need is just D1 plus D2. So just plugging back to the same example that I used before, in this case, you can see all I need is only 255 delays, for this cancellation loop. So this one just to show you that, this is this proposed technique is very modular. So you can actually use the way that you can cascade a different module to take care of different series of spurious tones. Okay, so shown here is the block diagram of this implementation. So basically the key point is to see this block right here. It will be inserted after this TDC output, and after you subtract the frequency accumulate offset, and you will go to this block and you subtract it out before you go to the digital loop filter. So that's the key block right there. Okay, and then this one just to show you the implementation of the averaging. So basically you would downsample it, and then you just keep accumulate, and you divide by however sample that you are trying to accumulate, and this is basically doing the averaging. Okay, so this is the integer MO. And earlier I mentioned that, what if the spur, is not integer multiple of the reference period? Sometimes it can come in a fractional relationship. Okay, especially in the case where, it is coupled, externally. So in that case, we could actually use this, some kind of fractional delay. And then this one, we can sort of use the multi-modulus divider, concept. So you can basically, sometimes divide by m, sometimes divide by m plus 1. So in this particular example, let's say if I want to delay by 10.25, so what I would do is that, in the first 3 cycles, I would delay by 10 samples, and the fourth one, I would delay by 11 samples. So you can see that, the error energy here, the difference here will be much smaller than, for example, if I always divide by 10. So you can see that this error right here will get accumulated by too much. Okay, so this is a very similar concept, as that, multi-modulus dividers. Okay, so this is a diphoto of that multi-tone feedforward cancellations. And then here, I just want to show you some of the measurement results. So this, first of all, we actually avoid any, interference. So there's no interference in the system, and there's no cancellation. And you see that this is the measured phase noise. And then we would enable the cancellation loop. So the reason why we show this, even though there's no interference in this case, we just want to show you that basically those cancellation loop that we added, it will not introduce additional noise to the system, even at the absence of any interference. All right. Then I want to show you that those averaging, effect. Remember that, I mentioned if we don't do the averaging, we could be enhancing the DCO phase noise. And then here's the proof. So we can see that, if I, only do averaging over 2 samples versus, I do averaging over 32 samples, you can see that whenever I don't do enough averaging, after the cancellation, you see there's a noise enhancement, which is shown in gray right here. It will get enhanced, as opposed to if I do enough averaging by 32 sample, you can see that the phase noise profile, go back to what we expect. In this prototype, we also, try to minimize the coupling of the reference clock. So that's why you can see that, the reference spur is really low. It goes from -110 dBc to -116 dBc. It's actually this is a very good performance, compared to all the state-of-the-art PLLs, as we can see here. For the Fractional-N spur performance, as we can see here, before and after the feedforward cancellation, we can see that before the cancellation, it can go as bad as -40 dB. And after we do the cancellation, it goes from -73 dB and all the way to -119 dBc. So it depends on the location of the spurious frequencies, the Fractional-N frequencies. Okay, so as I mentioned earlier, all the spur cancellation techniques, it doesn't really care it's coming from internal or from external. So here we also do experiment where we inject the spur externally, And we can see that, after we enable the cancellation, we can also reduce that spurious tone energy. Okay, here is an example where we, inject 2 series of the spurs. Remember that, when the spur frequency are not coming in a harmonic relationship. So this shows that, as you can see, before we do the cancellation, we can clearly see that there's a first series of spur right here and here. And then we also have the second series of spur right here and here. And now after we, enable that 2 loops that cascaded for the spur cancellation, we can see that all this spurious tone, they all go down, to the noise floor. So that just proved the effectiveness of the those 2-stage cascaded spur cancellation. Again, this shows the comparison with the state-of-the-art, and as we can see here, you can actually achieve a pretty decent fractional spur performance, and this is also to show that we can achieve this external spur rejection. Compared to others topology, you can only do this traditional analog isolations. And as you can see here, the reference spurs, can achieve a pretty low level. Next, I'm going to show you a more extreme case where the PLL can be potentially pulled by another aggressor. The reason I like to talk about this scenario is because today, a lot of our implementation is actually in SoC platforms, as we can see here. So there are just tons and tons of coupling paths, right? So as you can see here, this frequency synthesizer can get pulled by these digital processors. It can be pulled by this transmitter and receivers. They're all dancing together, on the same, silicon substrate. So this is becoming a really serious problem. And a lot of times what we do is that we just do a frequency planning. So for example, here, this is a known issues with so-called PA pooling. So in this case, let's say you have this transmitter, you have this PA, which is power amplifier on the same silicon. The problem with the output of the PA is that, the signal swing is very large. And then this large swing can actually find a path, either through the substrate or through the power supply, or it can be magnetically coupled to the oscillators. So no matter what you have, it always sneak through a certain path to actually interfere with your oscillator, or it can be actually, interfere with your input of the PLL. So this is one scenario. And another scenario may be that, there's another PLL right there, and then this oscillator may be coupling into the oscillator of the current designed PLL. So with that, as you can see on the right-hand side, when the pooling is happening, and you could actually degrade the entire phase noise of the phase lag loop. And again, as I mentioned earlier, a lot of times when people dealing with this, they just, try to design so-called as a frequency planning. So you will try to offset this oscillation frequency just so that, you can reduce this coupling between the aggressor and this victim, which is in this case is the oscillator. So that actually creates a lot of constraint because a lot of times, especially in the very complicated systems, it's just so hard to actually do a good frequency planning. Okay, so the goal here, is that since we kind of learn how to do this cancellation for the spurs, right? Doesn't matter externally or internally. Why don't we extend that to actually compensate for this pulling signal for the PLL? And note that, this pulling signal, can be a modulated signal. For example, the PA may be, transmitting some OFDM signals, right? So that aggressor right now can be modulation signals. Okay, but the good thing is that, because the transmitter is on the same silicon, so you actually know what is the signal that you are transmitting. So in many of these cases, the pooling cases, you actually know about the aggressor. But what you don't know is the coupling path, because the coupling path can be going to the substrate, can be going to the supply, can be magnetically coupling. So what is unknown in the system is actually the transfer function of this coupling, of this aggressor, right? So in this case, maybe the path going to the oscillator is H1 of omega, which is the DCO path, and for the reference path can be H2 of omega. So that's for the input path. Okay, so in order to do this cancellation or mitigate of the pulling signals, we need to somehow separate the two paths somehow. Okay, so that's why we propose this Dither-assisted scheme to actually separate the coupling mechanism of the two paths from the input and also for the output. So in this case, we would actually, dither the input clock by shifting the phase of the input, and then in this case, we can actually separate the disturbance from the oscillator and also from the input. So essentially, on the high side, the idea is that by doing this, I can randomize the pulling signal from the reference path, but I will keep the original waveform from the DCO path. So how does that work? As we can see here, this is the pulling signal, from the input path, and then as we can see here, because I'm actually shifting the rising edge of the reference clock, so I would actually, keep sampling a different part of the disturbance that's coming from, let's say in this case, the VDD of the reference clock buffers, right? So by shifting this, essentially I'm shifting a different part of the supply disturbance. So it means that, if you look at the output patterns, it's actually get randomized. Okay, so that's the for the reference. For the DCO, in this case, because we use the injection lock TDC, so it only affects by the rising edge of the DCO. So you can see that, it's only at the rising edge of the DCO will actually affect the TDC output. So in this case, no matter how I actually shift the rising edge of the reference clock, I'm still always sampled looking at the same DCO disturbance, which is injected by that pulling signal from the DCO supply. So that's why we can still keep the original pattern of the disturbance from the DCO. All right, so by doing that, right now, because we are able to separate the two paths, right? The input path we can randomize, but the DCO path we can keep the original pattern. So that's why, we can have this two cancellation loop. We have reference mitigation and DCO mitigation. So we can individually cancel out one by one. So for the input, once we dither it, we can cancel it right here to address the reference pulling. And then DCO mitigation loop is to address the DCO pulling path. All right, so here, just to prove that we can actually do that reference dithering and without affecting the DCO interference. So we show that, first we turn off the dither, right, which is shown in red, and you see the DCO right there. And then later on, we enable the dither pattern to the reference, and we can still see the DCO spur right there. Okay, so it just proves that, the DCO pulling signal will not be smeared out due to the dither. So this is very important because that's the fundamental of how this pulling mitigation can work, at the presence of a coupling path. Okay, and then here, if we actually consider the reference pulling, and then after we do the dither, we can see that we can, improve the spurious tone by as much as dB. And what about the PA pulling? As I mentioned earlier, right? If we use the PA, mimic the PA pulling signals, and then if we can estimate this coupling path transfer functions, and then we can see that the phase noise can also improve by as much as 2 dB. Okay, so this is again showing the comparison chart with the state-of-the-art PLL work, and you can see that, this is the first time that we can deal with the pulling signal coming from the DCO path or the reference path, or the combination of DCO and the reference pad. So this one just gives you a much more robust, solution, to deal with the. All right. So I'm almost running out of time, so I'll use the remaining few minutes just to quickly go over. There's yet another type of spur mitigation, which is based on the Dither. Okay, so basically the idea is that we know that spurious tone will coming in, and then if we just try to dither the clock going to this TDC time to digital converters block, we can actually randomize the TDC code at the output. So in other words, if that patterns get randomized, then we will see less repeating noise pattern that show up at the input of the DCO. So by doing that, we can mitigate the DCO. Okay, so the reason why we do this Dither approach as opposed to the spur cancellation, like this feedforward cancellation, is that in the case, for example, if I have a very fine frequency code, right, like 2 to the power of -10, then I have a spur period of 2 to the power of 10. So that's a very extreme case. If I like to use a feedforward cancellation, I'm going to end up with a long delay line. So in other words, this is a case where you have very, very closing spurs. So in this case, you could actually use this Dither approach, because for the Dither approach, you actually don't need to use that many flip-flops, right? So in this case, you just need to use a 5-stage flip-flop, or in this case, you just need to use a 20-stage of the flip-flop, and it will be much less than here. In this case, you have to use 1,000 flip-flop to generate that cancellation. Okay, so the way that it works is that, as you dither it, the signals, you would basically phase modulate that quantization noise pattern. So here, the quantization noise pattern is the sawtooth pattern that I showed you earlier, where you have the finite quantization for the TDC. So you always have this sawtooth pattern, and this is just a series, Fourier series expansion of that pattern. So what you're going to get is that you're going to get this phase modulate noise pattern and also a dither signals. So this phase modulate dither pattern is good, right? Because that's where we want to randomize it. But unfortunately, you also have this dither signal, which is very bad because it will add up to your phase noise at the PLL output. So what you would do is that we should also try to cancel this out. Okay, so we have shown before that we know how to do the cancellation right there, but the problem is there's a certain transfer function. So a little bit similar to the pooling signal, right? So the transfer function between the dither source and to this point, it's really depends on the PVT variation and the actual coupling path. So we need something to estimate the transfer function, going through this dithering and also the cancellation path. So we actually, propose, some adaptive filter, algorithm, so that we can estimate the transfer function of this coupling path, coming from the input, and also for the cancellation loop. So the idea is that, under all different PVT variations, we can match these two response so that we can have a good, cancellation. Here's a more detailed implementation, and just to show you how we can mimic that transfer function. So the bottom line here is that we just want to show you that all you need is just a 2-tap IR, and it can already show a pretty decent approximation to the actual coupling path. So we can actually adjust the coefficient right here of this 2-tap FIR, and we can mimic to match the coupling path transfer function. So for more details, please go to this paper. Okay, so here I'd like to show you some measurement results, and you can see that when I turn off and turn on the dithers, you can see that if I do the turning on and without cancellation, you see the noise floor will go up, but the spurious tone will go away. Right? So this is where we do the phase modulation on the quantization errors, but I still have that dither signals. So then later on, we can further cancel out that dither. So you can see that the noise floor of this blue right now is go down by quite a bit. And yet, all this noise energy of this spurious tone will also go away. So that would be the most ideal case where you enable the dither and then you actually cancel that dither. All right, so here shows a sweep of different fractional frequencies. And then by enabling the dither, you can see how much that this can improve. You can see that, it can improve more than 20 dB, and sometimes in this case, it's almost like 40 dB improvement when we enable the dither and also to enable that cancellation. All right, and then this one just to show you the conversion time of that adaptive filter, is roughly 1 microsecond for that cancellation. And again, this is a comparison chart with the state-of-the-art work, and again, this shows a pretty good reference spur and also a good Fractional-N spur performance. All right, so here I list a couple more works that related to this spur mitigation, and you can see that in one work they scramble the spur pattern of that TDC, and in another work they actually truncate the FCW, the frequency control word pattern, after the accumulation. And from there, you can also try to mitigate some of the Fractional-N spur that's due to the TDC quantization pattern. So for more details, please go to those papers, or if you have a question, you can feel free to ask me after this tutorial. All right, so in conclusion, the Low-Spur PLL are really feasible today, even if that's in the SoC platform when you have a lot of noise and basically aggressor nearby. We show that today there are PLL architectures and techniques that we can deal with those issues. And the second thing I like to point out is that there are really a lot of opportunities in the DSP domain to perform this kind of a spur mitigation, right? Or even for the pooling. So that's very important to recognize that the DSP opportunities. And three, I want to point out that today we already see a lot of examples that we can do direct spur cancellation, that we can tackle both internal or external generated spurs. And finally, I like to point out that the Dither-based is also another good approach. Basically, you basically have some trade-off of the slightly elevated noise floor, but you may actually reduce the hardware complexity. All right, so with that, here I list some of the references that I use for this tutorial. So feel free to go ahead and read them, and also feel free to ask me a question after this tutorial. All right, okay, so thank you for your attention for this tutorial. Okay, bye.
Thank you, Mike. That was a great talk. We have time for maybe a couple of questions. So others who have questions, please post your questions on the chat window, and we'll make sure that they get answered. So the first question is, when we use multiple delay-based cancellers, and when we cascade them, multiple adder blocks are needed in series. Will that limit the maximum bandwidth and the clocking speed due to the delay? Mike?
Yes, can you hear me?
Yeah, I can hear you now.
Okay, sorry, yeah, I just muted myself. Yeah, absolutely. When you do the cascading, as you can see, the critical path of that digital subtraction logic will unfortunately keep increasing. So it is absolutely correct. We have to be mindful that whatever that cascaded logic will not exceed the timing constraint of that digital block speed. So typically for the digital PLL, the digital block was clocked by the reference, input reference frequencies. So that's just one thing that we need to be careful that we create those we need to make sure that we can still complete the computation within the period of that reference clock.
Thank you. And another question was, how does the power consumption of these digital techniques to cancel spur compare to those in analog PLLs, where spur cancellation is done using analog techniques?
Yes, so it certainly takes power and actually the area consumption for those spur cancellation. So, for example, if you remembered, I showed the first prototype for the single tone cancellation. That one, by far, in our experience, is probably the most, power hungry and also area hungry technique. The reason is because we actually synthesize the digital sine wave. And also because we try to experiment basically the ideas, so we actually over design quite a bit, So those among all the spur cancellation, those are probably the most costly ones. But then when we look at the following spur cancellation, for example, for Feedforward, it's basically just come down to how much you want to do. Right. So if, for example, you have a lot of different series of spurious tone that you want to cancel and you want to cascade, so many different cancellation loops, then the power will add up. But if, for example, all you want to deal with is just the fractional-N spurs, and especially if this frac-N word is not super fine, so the delay will be more reasonable. It's not like thousands of delay right there. Then we found that the cost is actually quite reasonable. And again, even for that second prototype, we actually over-designed quite a bit. For example, we were actually trying to test the fractional delay also, because we were hoping to play that, to play with the sort of non-harmonic relationship of the external spurs. So that's why, we're just building a lot of logic that, was actually not necessarily, needed, for the actual product. But this is because it's a research prototype, so we just try to build a lot of knobs right there. And then the last one, yes, if you actually build the sort of the delta sigma modulator type of the PLL, doesn't matter if it's analog or digital. If you just do Dither, that will be easier, because you just basically based on your existing fractional dividers, and you try to randomize it. But know that whatever that you do, there's always a cost, right? Because in that case, you can actually increase the noise of that modulator, and sometimes people would also need to use additional cancellation loop to take care of those kind of noise. So in the end, I think it's just trade-off, and it really depends on your target application. I think in this particular tutorial, it just so happened that in the past few years, we really spent a lot of time just to see if the spur performance is really something that you care for this, for example, high performance systems, and those are the different techniques that we can potentially use, right? And then if you don't need that crazy spec for the spur level,
Hello,
you could
everyone. Welcome to tutorial session of IEEE CICC 2020. This tutorial is entitled Low Power PLL Architectures and Techniques.
Hello.
I'm Mike Chen from University of Southern California. My group mainly work on different critical components of analog mixing noise.
Hello, can you hear me? Yeah, I'm not sure. I was just hearing the presentation. Yeah, so the bottom line is that, yeah, it's basically different trade-off, for the different spur cancellation techniques. So are you still there?
Hi, Mike. So we have about 4 more minutes left for the next video, but I'm going to use the time for one more question, and people who need a break can step out and come back in 3-4 minutes. So a question is, how significant is the substrate noise in FinFET processes, and how does one even model it at the simulation level?
Right. Unfortunately, all our prototype was not in the FinFET processes. So unfortunately, I cannot provide too much information on that. But our experience is that even in the bulk technology, we actually don't know how much noise is coming through the substrate. So that's why if you check our approach, we always have some kind of adaptive loop to actually learn that coupling path. So to us, it's just a black box. It isn't some kind of unknown path. And then what we are trying to do is basically just to try to learn what is the transfer function looks like, and then how we can cancel it out. And that'll be the answer.